Alright guys, today we're going to be looking at our yet another problem under the backtracking pattern. Now this is the third pattern we have been looking at since our first pattern, which was the binary search pattern. Then we looked at a couple of questions under the DFS pattern. We also did a nice little intro for the DFS pattern, and now we are looking at the backtracking pattern. I have already done a couple of videos. If you haven't watched it, I would recommend you watch them before jumping into this video. So this would be a little bit of a medium level question under the backtracking pattern. This would allow us to understand backtracking and how we can use it in similar problems, and how we can utilize memoization specifically to solve something faster. Now let's dive right in. So the problem here says, given a string with digits from 1 to 9, return the total possible ways of decoding it. Well, we have a keyword right here which says decoding. They have also given us a meaning of what decoding is. Decoding has to be done using the dictionary, where 1 to 26 represent letters A to Z. So they're saying, let's assume you are given a dictionary, and something like 1 would correspond to A, 2 would correspond to B, and then so on until you have 26, which corresponds to Z. All right. So now we know what decoding means. So if we have digit 1 in our input string, we know that we can decode it to A, and if we have 1 and 2, we can decode it to multiple ways. Now let's look at how many different possible ways of decoding in an input string could be. I have had in an example here, which is 1, 2, 3. Now 1, 2, 3 can be decoded in at most 3 ways. Now why 3? Let's look at it. Now let's say our input string is 1, 2, 3. This is how I would like to solve it, right? You can either do 1, 2, 3 separately, which would be A for 1, B for 2, and C for 3, right? 1 corresponds to A, digit 2 corresponds to B, digit 3 corresponds to C, and so on. Now there's one more way to do it. We take 1, 2, 3 and we combine the first two, and then we leave the remaining out, and then we would have 12. So now what is 12 here, right? So let's count it, right? A, B, C, D, E, F, G, H, I, J, K, L. So 12 is going to be letter L, and then 3 is C. Well, this is one more way of decoding it, right? And well, there's one other way, which is we take 1, 2, 3, we do 1, we do 2 and 3 together. We leave 1 out and we do 2 and 3 together. We would get again A for 1 and then X for 23, right? I think W, right? All right. Okay. So 1 and 23 gets W. So you see there are only 3 ways. You can either combine the first two and leave the third one out, or you can combine the last two and then leave the first one out. And you have 3 different ways of doing it. Now, if you have, I don't know if you have observed already, but there are always, you have 2 choices to make, right? From an input string, you have 2 choices to make. What would those 2 choices be? Let's adhere to our backtracking solution template, and let's first try to convert this whole solution into a tree structure. So given 1, 2, 3, there are 2 ways, right? The one way is we have 2 options when we see the string. One option is to combine the first 2, right? And combining the first 2 would leave us with 3. Or don't combine the first 2 and just consume the first one. That would leave us 23, right? If it's getting difficult to understand, we are taking 1, 2 together. We're considering 1, 2 together. And in this edge, we are considering 1 alone. So we are left with 23. Now again, in these nodes that we have, 3 would be considered alone. So we are left with nothing. And similarly, we will have for 23, so 3, we are left with nothing, right? Let's look at 23. 23 you can either consume 2, right? Or you can consume both of them together, right? So you can consume 2, 3 together, or you can consume 2. So if you only consume 2, you're going to be left with 3. If you consume 2 and 3, you're going to be left with nothing. Now you see we are left with nothing in all of these cases. Now we have one more non-null node. So let's also look at it. You can only consider 3 here. So you're going to end up with an empty string. So you see there are total 3 leaf nodes that lead you to empty strings, right? And this is our solution, right? This is what we are trying to find. We have our string. We say, let's consider the first 2. What is left to be considered? 3. Let's consider only 1, only the first digit. What is left to be considered? 2, 3. Now for 2, 3, we're going to repeat that process, repeat the same process. We have 2 choices. Consider the first digit independently, or consider it with the second one, which is combining it with the second one. So you combine it with the second one, you're left with nothing. Well, this is one way of decoding it, right? This is number 1, number 2, number 3. So this is this whole path that you see, 1, 2, 3, 2, 3, 2, null. This is one way of decoding it. This is the second way of decoding it, and this is the third way of decoding it. All right, and I have also listed all of these ways here. Now that we have our tree, we also know what 2 decisions we need to make every time, and we also know that we have a dictionary. So let's just start coding it out, right? So step 1 was to create this tree. Step 2 is to write out our backtracking template code. So let's just quickly create a class. We're going to say encodings. Let's just give it a simple name here. And for now, constructor, I'm not going to be expecting much. I'm just going to be saying digits. So this dot digits equals digits. Let's just initialize our member variable, and then let's just create a function called decode digits, and the decode digits going to take nothing because it's part of the class. Now that it's taken in, we will still have to create a function called DFS. Well, we are just adhering to our backtracking pattern, right? Every time we create DFS, backtracking is nothing but DFS implemented, and implemented with a index. So DFS is going to receive a start index. I'm going to say if start equal, we'll just start with a very interesting base case, right? The base case in our recursive function will be now if the start has already reached the end of the digits, then we just need to return 1. Now start will be equal to the end of the digits only when we reach a null string, right? Which means we have considered all the digits starting from the left to right, and we are left with no digits to process. And so we return 1, because this is one valid way of decoding. All right. Now we want to do something like we want to first create ways. Right, now let ways be 0. Starting from the first string, we want to calculate the number of ways, right? So what would the number of ways be? We need to start this tree, right? We have the string, we need to start these branches. Now how do we start these branches? We need a dictionary which would tell us if we can start with 1, 2, or 26, right? If you look at 1, 2, 3, you know you can start with 1, you know you can start with 23 as well. Right, so you need a dictionary to check if 1 starts with a valid character or if 23 starts with valid character. So let's just also create a dictionary. This dot digits to letters is going to be a dictionary, and this is a dictionary right now. I would want to create it, so I would want to populate it. So I would say for let I equals 0, not 0, 1. I is less than equal to 26 because I have 1 to 26, and then I plus plus, and every time I just want to push it to. Now it's not going to be dictionary, it's going to be a list. Sorry, my bad. Now we're going to be pushing I dot to string. Now the reason we're going to be pushing in string is because we want a string comparison, because the digits input is a string, so every digit in our input string is going to be a character, and we need characters to compare it with. All right, now that we have populated our digits to letters list, we want to go through it. Let's say for let num of digits to letters. We want to say the first thing we want to do is it a valid path? It is a valid path. So say if, how do we check it, right? We're gonna do this dot. We're gonna say this dot digits. Not digits. We want to only get the remaining of it, right? So let's assume you are at this node. This node is just the second half of the original digits string. So you first want to say let remaining equals this dot digits dot slice start is going to give us all the characters from this particular start index to the end. All characters from start index to end. All right, and so we just need to say if remaining dot starts with in JavaScript is a higher order string function, which you can call on strings. Remaining is a string, and if it starts with this number in our dictionary, then it's a valid path. We can call our function. We can say ways plus equals whatever our function returns, right? This dot dfs, and you can pass in start plus you need to say num dot length. Now I know this length can will either be 1 or 2, because we only have numbers from 1 to 26, and we're just trying to get the number of ways. So remember, when we are calling a recursive function, every recursive call is going to fall within one of the pockets. I like to call these if condition pockets. So this is one pocket. So one of the calls could fall into this pocket. If it does not fall into this pocket, it's going to go through all of this, and it has to fall in one of the two pockets, right? So the default pocket is we have calculated ways starting at a particular index called start, and we're going to return it. So our caller always needs to receive a value, right? So there's one caveat with this kind of implementation. We'll look at it why. That's the time complexity of this is going to be 2 to the power n, and the reason it's going to be 2 to the power n is every time we have two choices to make, and there are n levels: level 1, level 2, and level 3. So in this case, it's going to be 2 to the power 3 because we have 3 digits, right? So the time complexity is going to be 2 to the power 3 for this particular example. To generalize it, we would say the time complexity would be big O of 2 to the power n. And 2 to the power n is exponential, and we don't want exponential, right? We want something that is kind of 2 to the power n, but not exactly 2 to the power n, because half of it can already be stored somewhere, right? We are calculating ways starting at a particular index, let's say 1, multiple times. And we can use the number of ways that we have already calculated thus far. We don't have to run this loop every time for all recursive calls, right? And that's where memoization comes in. So let's see what happens if we don't have memoization added here. So if we don't have memoization added here, this is a very simple vanilla backtracking implementation where we have DFS function. It goes through the very end, it creates all of these left nodes, and then goes backtracks, and then it starts with the right nodes, and so on. And trust me, this is going to work, but then it's not going to work for bigger examples. So let's first create let en equal to new encodings, and then let's just pass in the digits, right? It's passing 1, 2, 3. All right, so now it's going to work for 1, 2, 3. You'll see All right. And then we just need to say console.log en.decode digits. Just need to call decode digits. All right. Let's run it in our trusty online JavaScript compiler, and let's see what error we get. All right, it's saying undefined. Okay, because we haven't called our DFS function. Now DFS function needs to start at 0, and that's all. And then whatever DFS function returns to us needs to be returned back to the original caller. All right. DFS is not defined because we aren't using this keyword. This is the DFS. All right. Starts with is not a function because there's a typo. Starts with, okay. 3. So there are 3 ways we got our output. Now, what if I change this to say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. It's just random numbers, right? It's almost impossible to calculate the number of ways manually, and so we're going to rely on this. And you see, it's taking almost forever, right? The first example took only about a second or two, and this is taking too much time, and probably it's going to time out if you try to run it in some other compiler. So what's a solution here, right? You got my point. When we pass in a huge input, it's going to fail. All right. We still don't see an output, so I'm assuming it's timed out. Okay. Now it's timed out, and how can we kind of improve this to the power n? And using memoization, right? So you see, we have this number of ways. I'm calling it ways here, right? And we are calculating it almost every time, starting at every index, right? This kind of has this fancy tree structure to us, right? And we need to store these ways somewhere. So let's say we have a memo, and what if I just store this value in the memo? But before even storing it, I say if start in memo, then all I need to do is just return memo start. Now what does memo start store, right? Memo is a dictionary, and the start is going to store the number of ways of decoding the digits string up to the start index, right? And so I just need to store it here. And once I calculate the number of ways starting at start index, I'm just going to store it here, and then I can return memo start. Now I don't have to do this. I don't have to calculate this whole thing for recursive calls where I already have this. So we have this new pocket in our recursive function. Now one of the recursive calls is going to fall into this pocket, and we're going to save a lot of time, right? There's no redundant work that we will be doing, right? So one last thing that we need to do is we need to say return DFS, this.dfs. Let's just pass in start at the 0th index and pass in an empty dictionary. We'll be passing it along, so we need to pass it in every call that we make. So once we have done that, we just need to copy all of this, paste it, run it. Now it's going to be faster. Let's try to put in something similar, a huge input. Let's see, we get an answer. We got an answer. Well, all right. So as you can see, we used a simple dictionary, and then we passed it along in every call, and then tried to pass in a huge input string, and we still got our output. Well, this was about memoization and backtracking. I'll see you in the next one. Until then, happy coding.